Okay, good morning, guys. Okay, so we have seen what is transverse fillet and what is parallel fillet. We try to understand what is the basic difference between these two fillet joints. In one, force is parallel to the plane of the weld, or the fillet, or the lap of the weld. Okay, and in others it is perpendicular. So we have seen in obviously in the case of when it is parallel, the stress which is a stress which is caused in the weld is shear stress, and in case of transfer, the stress which is caused in the weld is direct stress or tensile stress. Okay, so sigma t will be using in that case. So we have seen formulas for those. We have also seen, no, we have taken a couple of numericals on that. Okay, so we have, I think, finished up to this part, and today's lecture. So this is eighth lecture for this unit. Total there are 10 lectures dedicated to this unit number 5, and we have 3 more units today and 2 more units, and we'll try to finish the syllabus of the welded joint. Okay, so now we are slowly shifting. We have gone through the basics of what is welding, what is stresses in welded joints, and basic stresses in welded joint: transfer, fillet, parallel fillet, butt joint. Okay, so we know the basics. Now we will go little bit advanced design. Now advanced design means now the joint will remain same. The stress in lap joint, or all those will remain same. Only thing is that the weld, how we are putting the weld, that is get little bit complicated. So it is kind of advanced design, where not only the direct stress but also the stress because of the eccentricity and momentum comes into picture. Okay, clear. So now we will today will see actually loaded asymmetrical welded joint. Now when we say asymmetrical, that means it is the welded joint is not symmetrical. There are main 4 topics we would like to cover. Okay, let me just quickly open the syllabus. I would like to show you what are those 4 topics, and we will try to cover those in the remaining lectures. Okay, where is that unit number 5? Okay, so let me just stop share this. So quickly we are going through. I'm just trying to go take you through the syllabus also. So obviously all topics and threaded joints are completed. In welding, symbol is completed. Stresses in butt and fillet welds, we have seen that. Butt parallel transfers, we have seen that in last lecture. Actually loaded asymmetrical welded joint, today we are going to see that. Now which is actually loaded, but it is asymmetrical, means it's not symmetrical. The welded joint is not symmetrical, it is not equal on both sides. Then eccentric load in the plane of welds. So there will be eccentric load will be eccentric, or in the plane of weld, means in the wherever you are putting your plate, in the same plane we are have load, but that load is not at the center, it is eccentric, like we have seen in the threaded joint. Okay, and then the last 2 topics are bending and torsional moment, where we have welded joint subjected to those. Okay, so there are 4 topics, and we are trying to cover today this asymmetrical welded joints. Okay, got it. So as I said, we are trying to cover each and every topic. So now what is actually loaded? So member is loaded along the axis of the plate, right? So load is what you can say, along the axis. It is not eccentric, means it is not away from the plane of the weld, but it is actually loaded, but the weld is asymmetric. Okay, so we try to understand. Now this is actually, take a look at the diagram. If you can see, there is L angle is welded, at the top and bottom. Okay, but the weld, one weld length of weld 1 is less than length of weld 2. So this is now asymmetric, it is not symmetric. If the symmetricity is there, then your design becomes quite simpler. But when asymmetricity, then there we have to consider the moments, we have to consider the center of gravity, because center of gravity will not be at the center. Now assume that 1 and 2 are same. The weld lap, or the fillet you have put here 1 and 2 is they are same. Then the center of gravity will be at the center, and your calculations will be very easy. But since the areas are not same, then the obviously your center of gravity will be, it will shifted, and your calculations will change. Okay. Now just try to tell me what kind of stresses will be in the weld. First of all, try to understand that what kind of stresses will be in this weld. Okay, now there is a L angle is there. Okay, So we have in that L angle, top part and bottom part is welded. Okay, if you see the side view, and the G means the G is the center of gravity of the L shape. It is somewhere in the at a distance y1 from the top and y2 from the bottom. Okay, the center of gravity is not at the center line of the this L angle, but it is little bit downwards, because there is a extra what you can say material at the bottom part, because it's a L angle, right? So center of gravity is shifted by the distance y1 from 1 and y2 from 2, and now we have to calculate the what strength of this. So just try to take a look at the diagram. See, in the third diagram, B diagram, the only this thing are the welds are shown, and now you have to understand what kind of stresses will be there. Just try to imagine now. So first of all, tell me whether this is a transverse joint or it's a parallel joint. Just try to look at this welds and tell me. You can put in your chat what type of weld is this. It's a obviously it's a fillet or lap joint, but it is a transverse fillet or it's a parallel fillet. Tell me that. What kind of fillet in the diagram, B or A? What kind of fillet? Just put in your chat. I want to see whether anybody is listening to me. Whether it's a transverse fillet joint or it's a parallel fillet joint. Anybody can guess? Okay, I have one somebody. It's a parallel fillet joint. Why, Ravi? Ravi, you are absolutely right. And why is the why that is the case? Because yes, Nikita, it's a parallel fillet joint because the lap or the fillet is parallel to the forces, right? It's a parallel to your load P, right? Because the load P is in the axis, along the axis, and it is parallel, so it is a parallel field. Absolutely right. Okay. So now, what kind of stress will be there? Now, just imagine you have a triangular kind of shape, weld is there, and you are pulling it from the both sides. So it will be what kind of stress will be there? Obviously, it will be shear. Top part will go top, bottom part will come down. Where the area is minimum, the shear will be there. So obviously, there will be a primary shear in both the areas, right? The shear stress will be developed, right? And now there is, along with this shear stress, there will be also what you can say, moments also are created. Now because now see the area or the load in each part will be different. Now, if the both the areas are same, area 1 and 2, then load will be equal and your calculations will be much easier. We can simply calculate by using this formula. Load is equal to 0.070 HL1T. If L1 is equal to L2, then we'll simply put 2 into 0.707 HLT, and that times it is twice. Your strength is double compared to one whale, right? So it is very straightforward. But since the areas are not same, then because of this load at one, load carried or load taken by one will be different than load taken by two, right? You agree? Since the areas of the wheels are different, that's why it is called asymmetric, right? So we are having axially load, so load is along the axis, asymmetrical welded joint. So it is not symmetric because the areas are not same. They are not at the symmetry. They are not symmetric. So because of that, what happens? So because of that, load taken by area 1 will be different than load taken by area 2, right? Because the areas are different. So we have to find out what is the load taken by area 1 and what is the load taken by area 2. Very simple, straightforward problem, right? It is not difficult, just you need to understand the concept. Okay. So now we have a case where the load is axial, but the weld is asymmetrical. And now we have to find out what is the load taken by P1 or area 1 and area 2, and accordingly we can calculate the length L1 L2. Okay. Okay. So now how we can find that out? What is the area taken by area 1 and 2? What is the load taken by those? Now we know one thing, that by direct we have, as from the formula of the fillet joint transfer, parallel fillet joint, what is the P1 load in area 1? It is 0.707 HL1T, right? You agree with that, right? Since this stress developed, this shear is tau, length is L1, and your H is the thickness of the weld, then a load in area 1 is 0.707 H1 HL1T, right? Agree? Similarly, load in area 2 will be 0.707 HL2T. So now P1 is the load taken by area 1 and P2 is the load taken by area 2, and total load should be equal to P. So it's very clear now that P is equal to P1 plus P2, or we can say 0.707 H tau is common L1 plus L2, right? So simply 0.707 H into bracket L1 plus L2, length, total length of the weld into tau will be your total load taken, right? Okay, so that will be the total load taken by the your P1 P2. But now, if we want to find out what is the length, or the proportion of the length, then we can say, because of this load P, as I said, there will be a moment, or load P is, see why there will be moment, because the load taken by one P1 is not at equal distance from the center of gravity, since the center of gravity is not at the center of the plate. Are you getting my point? Since if the distance y1 is not equal to y2, then P1 moment, say at the center of gravity, the moment will be P1 into y1 and moment is P2 into Y2, right? And we, for equilibrium, we should have this moment balance. So we can calculate the load taken by each of, if we know the lengths, then we can calculate this load taken, or we can calculate the lengths or the load taken by all these areas by using the balance of the moments. Since this whole assembly is in equilibrium, the moment because of the area 1 or the moment because of load taken by area 1 equal to moment equal to load taken by. What is those moments? P1 into Y1, P2 into Y2. So simply we can compare, P1 Y1 equal to P2 Y2. Now, this we can put this value HL1T, or by putting this value we can get L1 Y1 is equal to L2. So P1 is equal to 0.707 HL1T. H and tau are constant. So only difference is L1, L2. So those will cancel out and we get L1 Y1 is equal to L2 Y2. All right. So now from this we know now there are two things. First is L is equal to L1 plus L2. Total length is equal to L1 plus L2, and L1 Y1 is equal to L2 Y2. So the distance of your weld from this center of gravity multiplied by length of the weld is equal to say similar moment from the other way. Okay, so by using this equation we can calculate the lengths and loads and all that, right? Clear? Any doubt anybody is having? So this is the case where the weld is asymmetric, it is not equal length, it is asymmetric along the axis. So because of that there will be a shift in the center of gravity and there will be moment. Okay, so if you guys are okay, I can proceed with the numerical. Okay, so with the numerical, we will get a better picture now. Now it is saying that an ISA a standard angle is there, 200 by 100 into 10. Now 10 is the thickness, right? 200 is the height and 100 is your the L portion which is coming outside. What does that? That's what we mean by these numbers. 200 is the height, 100 is the L projected outside, and 10 is the thickness of your angle. Is welded to a steel plate by means of a fillet weld as shown in the figure, right? So now we know that there is a fillet joint and it is a parallel fillet because it is, the fillet joint is parallel to the force. The angle is subjected to static force. The load applied to the this assembly is 150 kilonewton, and the permissible shear stress is given as 70 Newton per meter square. Okay, to determine lengths of the weld at the top and bottom. Okay, so simply we have to find out length what we should give here and length what we should give here, L1 and L2. So we straightforward. Now we with this whatever design we have seen just now, we know that L1 L is equal to L1 plus L2, right? L1 Y1 is equal to L2 Y2, and P is equal to P1 plus P2. So using these formulas, we can find out L1 and L2, the lengths, of the weld required for this kind of design, right? Okay, clear? So what is given now? First, given P is equal to 150 kilonewton, allowable shear stress is tau is 70 Newton per mm square, and the plate is this angle dimensions are given. Okay, so let's calculate now total length. So obviously, total length given is P 150 kilonewton. Tau we have noted all these down. H is the thickness of the angle. that is equal to obviously thickness of the plate, means that will be the thickness of the weld also. Okay. So total length of the weld, first, now this load total length should be equal to able to take the load of 150 kilonewton. So we directly get this formula, P is equal to 0.707 HLT. We can calculate the total length required. So that length is equal to L1 plus L2. So how we can calculate this? Then P is equal to 0.707 HL tau. We know P, we know H, we know tau. We can calculate total length. So by this formula, we put the value of P 150 into 10 raised to 3, 0.707 into 10 into L, length we have to calculate. Now this is not length 1 on length 2, this is the total length, and means then we have to calculate L1 and L2 individually, but first we will try to find out what is the total length of the weld required, right? So total length required is 303. We come down to L is equal to 303. Okay. So now that means to take this load, we have to have like total length of the weld of, if we can have 303, then we should be able to this, or this assembly will survive and it will not fail. Okay. Okay. Now we'll proceed now with the finding out the individual dimensions L1 and L2. We know now total L is equal to L1 plus L2. So we know L is equal to 303. So out of that, some part will be L1 and some part will be L2. And now we know that L1Y1 is equal to L2Y2. L1Y1 is equal to L2Y2. Now they have given, like in the formula, center of gravity. Actually, if it is not given, sometimes we have to calculate it by using the area, right? We'll use this area, and then we will find out the center of gravity by using the different kinds of theorems, right? But they have given the center of gravity is 71.8 from bottom, right? And total distance is given as 200. So from the top it is 128.2, whatever it is, right? So it is 200 minus 71.8, so it becomes 128.2, right? So we know why this distance y1 128.2, we know this distance 71.8, and we know L. So we can calculate L1, L2. So there are two relations. L is equal to L1 plus L2. It is 3,303, and this L1 into Y1. Y1 is what? 200 minus 71.8. So I calculate 128.8, right? Now this is not 128.8. This must be 128.2. A typing mistake from my side. So 128.2 is equal to L2 Ly2. L2 is yeah, we have to calculate. Y2 is 71.8. So what is Y1 Y2? Distance of the center of gravity from the top and bottom welds. Okay. So using this, we can calculate a relation between. We can find a relation between L1 and L2. So L1 is equal to 128 divided by, or L2 is equal to 128 divided by 71.8 L1, that many times. So put those values here and we'll get L1 is equal to 108.81 and L2 is equal to 194.2 mm, right? So we calculated different lengths by using simple formula, moments, right? Moment because of the area 1 should be equal to moment because of area 2 at the center of gravity. So area 1, P at area 1 multiplied by distance of area 1 from CG is equal to P at area 2 multiplied by this distance of that area 2 from CG. Got it? So yeah, using this relation and using L is equal to L1 plus L2, we can calculate different lengths. So we got L1 is equal to 108. So this will be 108 and this will be 194. Total length will be 303, right? So that the total length will be able to take the total load and also the moments will be balanced. Clear? How the with this example, the concept gets pretty much cleared. Okay. Anybody has any doubt about this? It's easy to understand, but only thing we need to understand is that it is a asymmetric. Asymmetric, it is not symmetric along the axis. Okay. Okay. Simran saying no, sir. So I don't know whether she is saying no to she got it or she don't have any problem. Simran, what do you mean by that? You are saying no, sir. That means you have no what you can say questions, or you did not answer, no doubts. Okay, good, awesome. So Simran has no doubt. Anybody has any doubt, you can ask me. Chat. I'm keeping watch on chat also. But with the numerical, it should be pretty clear to understand. Okay. So if there is no doubt, we can proceed with the next part. So out of 4 topics, I finished the one topic, that asymmetric load, right? But it is parallel to the axis. So this part was actually loaded, right? Asymmetric welded joints. So the welded joints are asymmetric along the axis. The lengths are not equal. The way what we are, simply we have to calculate L1, L2. At that time, we will take the moments of area 1 into distance of that area from CG. Similarly, equal to area 2, the moment of that area 2. If we have 3 wells, say like one small, another small, and one long at the bottom, we will use the same kind of concept, right? So moments should be balanced. Okay. So let's now slowly move to eccentric load. Now we are going what we did in case of threaded joints. Eccentric load, but it is in a plane of welds. So eccentric load means what? The load which is not at the CG, load which is away from CG. So because of that, what happens? Can anybody tell me? If the eccentricity, we have seen this in a threaded joint. If the load is eccentric, means it is not at the center of your gravity. Because of that, what will happen? What kind of problem will be there? Can you tell me? Can anybody tell me? We have seen the same thing in a threaded joints also. We have eccentric load in a plane of weld. So where we have those, plane of weld means what? Now say we have 2 welds, right? In this case, we have 2 welds. So if we take a plane which is going through both these lines, it will be a parallel to this plane. Okay, are you getting my point? It is a parallel to this plane, right? So we have a load which is in this plane. So load will not be like this. Load will be like this, but it is eccentric. Eccentric means load will be like this now. So load will be on the plate, but it will be not at the CG, it will be away from CG. So now if that is the case, eccentric load, so what comes into picture? Can you tell me? Because of eccentricity, what happens? We have seen this in a threaded joint. The load is not at the CG, because of that, what happens? We have to consider now what? Can anybody tell me? Because of the eccentricity, what comes into picture? Nobody? Okay, so I'm not getting any answer. So what we did is that, because if the eccentricity is there, we will have this, if the distance is E from the CG, we will have a moment because of that load, right? And that moment has to be balanced by the moment from the your 2 different or your wells, right? So your wells will have different kinds of moment, and those moments. So like if the eccentricity on the right hand side, we'll have a clockwise moment because of the eccentricity, and that has to be balanced by anti-clockwise moment in the well. So well will have moments, and because of the moment, obviously, if the moment is there, we'll have a shear stress, and that shear stress we call secondary shear, and obviously there will be a primary shear by using this formula, right? 0.707 HL tau, right? So now we have 2 stresses. One is primary shear, one is secondary shear, and then we will combine those. Are you getting my point? But we have seen this in the threaded joints also. But I doubt you must have forgot about that now, because there are 3 4 lectures has gone and it is wiped out, right? But anyway, so we'll go through now. Now let's take, now see, as I said, this load, now this thread, your welded joints are, right, are like in the top and bottom, W and W2, but G is the center of gravity of that. And your load is in the plane of the weld, but it is not at G. If it is at G, then we will get simply shear stress, right, direct shear, right? But since it is away from this, then we will get a moment M, right? So we'll have moment M, and it now see A is in A we have only simply force P, load P, which is eccentricity E, but in B it is shown now what is the effect of that at the, so at the center of gravity we have two different kind of loads or stresses. One is direct load P, obviously we have seen that direct load P, and because of the eccentricity there will be moment M, and we have to have balance of both these. So because of P there will be direct shear, and because of M there will be a moment which has to be balanced, right? So we can resolve this case in A, we have 2 wells and the load is at eccentricity E. We can resolve that to addition of 2 things. One is load P plus moment M. Are you getting my point? And that moment M is equal to load into eccentricity, P into E. Okay, clear? Now, I don't think you will have any doubt how to solve a eccentric problem. It is the same what we did in the case of uh, what you can say in threaded joints. Okay, it's similar kind of problem is there. Only thing is that here we have to resolve the load. See now, if the load is at G, what will have will be what are the stresses in the welded joint? Simply shear stress is equal to P upon area, right? Area is your minimum area, 0.070 into L into H, right? Okay. So if the P is at G, then you will have simply tau is equal to P upon A. But since it is at a eccentricity E, we'll have moment P into E, and we have to balance that also. And that moment has to be balanced by the moments in the wells. Okay. And we'll see that. Okay. But are you clear now up to this now? Because of the eccentricity, we'll have two different types of stresses. One is direct stress because of load P, as shown in C, and one is because of moment, there will be a secondary shear. Okay. So now direct shear will be tau will be P upon A. So direct shear in the welded joint is P upon A. P is the load and A is the area of the welded joint, right? So it is a throat area. So 7.707 H L, that will be your area. Okay. Now we will come to the moment part. Now we have to find out the moment, how the moment is balanced. Okay. So now see, okay, now we are going in the secondary part. Now second shear stress, that is tau 2, that is the secondary shear stress. Okay. As I said, same thing we did in a threaded also. We have two stresses, primary shear stress because of direct load P and secondary stresses because of the moment. Moment, okay. What is the formula for that? Tau is M upon J is equal to tau upon R. We know that formula, right? This is a torsional stress, right? M upon J is equal to tau upon R. M is moment upon J, polar moment of inertia, is equal to tau upon R. So with that equation, we get tau is equal to mr upon J. M is moment, R is radius or the distance, J is polar moment of inertia, right? So we have to find out M. We know that M. What is M? P into E, right? Moment is P into E. Now R is distance, J is polar moment of inertia, right? So we have to, for each, now there are, see, W1 and W2 are two welds. G is the center of gravity, okay? So now tau, what is tau 1? Tau 1 is the direct shear stress. How the direct shear stress will be there? It is perpendicular to the, what is your axis of your weld, right? It is shown in the diagram A. But tau 2 will be now, as we seen in the threaded joints also, perpendicular to the, your radius, right? So if we say GA, okay, is the A is the secondary, tau 2 is the secondary shear stress at point A, then GA perpendicular to that will be your secondary shear stress, and then we have to take tau 1 and tau 2 primary shear stress secondary and calculate resultant tau and use that for our design. Are you getting my point? It's not very complicated. It's the same thing what we did in a threaded joint also. Only difference is that there was four separate, but here is the welded. Now why I am taking the only this distance? Because it is the maximum distance. The stress at anywhere in between will be less. Are you getting my point? So distance which is the maximum, this extremes of the, or the ends of the welds, we will take that for our calculation, right? So now we have two stresses. Again, I will repeat. Because of the eccentric load, we have, because of P load, there will be a direct shear, which is given by tau 1 is equal to P upon A, right? That will be going upwards if the load is downward, going downwards if the load is upward, right? So it is taken here, and because of the moment of the eccentricity, the moment will be P into E, and that will be balanced by the moments in the welds. And how we can calculate those stresses because of those moments? Tau is equal to M into R upon J, right? So we calculate this tau, and the direction, now see this, we have to do a vector calculation. So tau is perpendicular to the radial distance, right? So tau will be like this. This is tau 1, tau 2, and then we'll get a resultant of those to get the resultant shear stress. So the resultant shear stress tau, yes. Time lecture होते हैं. Okay, resultant shear stress tau is equal to tau 1 and tau 2 vector addition of those two. Okay. Clear? Anybody has any doubt? It is I'm trying to explain in a slow manner. So again, because of the eccentricity, we are taking an example of eccentric load at a distance e from the center of gravity. We have direct shear and secondary shear. Direct shear because we take the load at the CG, it will be directly sheared, right? And because of this moment, we'll have a balancing moment, and that moment is given by tau is equal shear is equal to m into r upon j. Okay. Now we have to find out. Now what we have? We know direct shear tau is equal to P upon A. We know P, we know A. We can calculate this, no problem. Now here we have to find out tau. Tau to secondary shear. It is equal to M into R. We know R. R is the distance from CG to the end. We know R. We have to find out J. Now how to find out J? Polar moment of inertia of your area, right, of your polar moment of inertia of your area at the around at the CG, not at the CG, at the CG, and that is the part which we have to understand. Now how we will calculate that polar moment of inertia? That moment of polar moment of inertia is given by, we have to first of calculate the moment of inertia along x, y, right, and then add those two to get the polar moment of inertia at the. Now see first, try to understand how to calculate the polar moment of inertia of this area. Now concentrate on area 1 only. Okay. Now area 1A, right? So there we will calculate the polar moment of inertia at the CG. Where the CG will be there, if we draw axis like this, x and y axis, we'll have CG here. Along that CG, the polar moment of J is equal to Ixx plus Iyy, a perpendicular theorem, right? So what is Ixx? For a rectangle, what is the moment of inertia? BD cube by 12. B d cube by 12. So Ixx will be, so now take this area now. Okay. So now we are considering the area 1 and we are trying to find out its center of its polar moment of inertia, right, at its own CG. So if G1 is the CG of the area, then Ixx will be BD cube. B means this dimension. If this is the axis, BD cube. So L into T cube by 12. Got it? So Ixx of this plate will be L into T cube by 12. L is the length, T is the thickness. So L into T cube by 12 will be its Ixx, and Iyy will be T into L cube by 12. Got it? In that case, this will be T into L cube by 12. Okay. So we get J is equal to J at G1. So why we are putting G1 here? Because it's not polar moment of inertia at the center of gravity of the plate. It is not about this point G. It is about its own center of gravity, right? So JG1 is equal to Ixx plus Iyy. And since now see Ixx we got LT cube by 12 and Iyy TL cube by 12. But since T is very small, it is compared to L, this thing will be very small because there is a cube of this, right? Obviously, length of the weld is generally very large compared to the thickness, right? So this Ixx will come down to very small thing because the cube of there. With this is basically L into T into T into T, right? So this will come to small, but this is T into L into L into L. L is large. So Iyy will be very large compared to Ixx. So for our calculation is, we'll take Iyy, right? So now polar moment of inertia, right? Polar moment means what? It is perpendicular moment of inertia, right? So Gj1 is equal to TL cube by 12. So here we'll take T into L. Same thing, we'll just take L cube is equal to L into L square. Why are we taking this? Because we want to take area outside. And why is that? Because we will see that in the next step. Taking area out is easier for our calculation, right? So what is the area of this plate? It is equal to T thickness into L. So we'll take TL out. So that is A L square by 12. So basically it is same thing. TL cube by 12 is equal to AL square by 12, right? So polar moment of inertia of the plate along its CG is AL square by 12, right? So we got that, but we had to calculate the polar moment of inertia from where? From this CG, not. So we got the polar moment of inertia along its own center of gravity G1, but we want along G. Now what we can use? We can use a parallel theorem, right? So we can use parallel theorem. So we know what is that. This is the parallel theorem. Polar moment of inertia at G is equal to polar moment of inertia at its own axis plus area into distance of that from the CG, square of that. Okay. So Gj is equal to, you know, this is a parallel axis theorem, and this was a perpendicular axis theorem, right? So what parallel axis tells you that center of gravity along any its own of the assembly is equal to center of gravity along its own axis plus its area into distance from the center of gravity, right? So here we know that Gj1 we just calculated AL square by 12 and into AR1. R1 is what? Distance of its from the CG, right? This is the distance, right? So we know that, and we from that we can calculate. So that's why I was telling that why we need area, because here we can take area outside, so it will become J at center of gravity along the CG of the assembly is equal to area into L square by 12 plus R1 square. Got it? So similarly, like if we have, you know, different areas J1, J2, polar moment of inertia, then we can calculate those using this formula. Got it? So it is what you can say. Only thing is finding out the polar moment of inertia along the along its center of gravity of the assembly. We will use area of the weld into L1 square upon 12 plus distance of the extreme distance, of the maximum distance of the weld from the CG. Okay, and once we know that, we can put those J here. We know moment, we know R. We can calculate secondary stresses, and then vector addition comes into picture. We can calculate tau, and that tau will be allowable shear stress, and then we can get the all those, you know, length of the weld, all those information. Okay, clear? So it is almost approach is exactly same what we seen in the welded threaded joints. We have to now there are, as I said again, I am going quickly. We have two shear stresses: primary shear stress because of load P, and secondary shear stress because of moment M. Secondary stress is tau is given by mr upon j. Primary shear stress is directly load upon area. Secondary is given by mr upon j. Here we need to know what is j, polar moment of inertia of the area, right? So there are, since there are two areas, so we will have addition of these two. Polar moment of inertia will be whatever we get here multiplied by 2. And how we can get this? Polar moment of inertia of along the CG is equal to polar moment of inertia along its own axis plus A into R1 square, and we can get this, that is polar moment of inertia Gj is equal to area into L1 square by L square by 2 plus R1 square, right? Once we know that, we can calculate tau 2, then use again this